Hello students, now we are going to study about Kepler's laws. We know the three laws of Kepler. First one, which is each planet moves in an ellipse with the sun at one of the focus. Second is the radius vector from the sun to a planet sweeps out equal areas in equal time. And the third one is the period of revolution t of a planet about the sun is related to the major axis of the ellipse A by the relation t square is equal to ka cube, where k is the same for all planets. In these three, the first one we have already studied in the last video, in which we have discussed the planetary motion or the orbits of different satellites. Okay, it was discussion of the first law. And we have already studied about the second law from the general features of central motion. This second law is readily explained in the general feature of central motion. In this video, we will be studying about the third law and its proof in detail. So the third law is the law of orbits. The Kepler's law is easily proved by a small trick. Okay. You know the equation for angular momentum L is equal to mu r square d theta by dt. Okay, in this equation you rearrange this equation in this form by multiplying 1 by 2 on both sides and taking mu to the left hand side. So you get it left hand side as L by 2 mu dt is taken to the left dt. So L by 2 mu dt is equal to half r square d theta. So you have RHS in terms of differential of theta and other with left hand side with respect to time. Okay, now what is half r square d theta? So you look into this figure, you analyze this triangle. Okay, this is the radius and this is d theta. So this arc is approximately equal to the path followed by the satellite, right? This r d theta. So what will be half r into r d theta? That will be half base into height. It will be the area of this triangle. Okay, so right hand side is a differential element of area in polar coordinates. So you got half r square d theta as the differential element of area in polar coordinates. Now over one complete period, the whole area of the ellipse is swept out. Okay, so you in this equation dt is replaced as capital T, which is the time period of the satellite. So left hand side becomes L by 2 mu T, that is equal to the total area of the ellipse. It will be equal to pi a into b. A is the semi-major axis and b is the semi-minor axis. We know the total major axis is capital A, therefore small a is equal to a by 2, which is called the semi-major axis, and b is the semi-minor axis, right? Now we have the relation capital A is equal to C by minus E. Okay, therefore small a, which is the half of that, it is equal to C by minus 2E, and B, which is the semi-minor axis, is equal to L by root minus 2 mu E. You can define or you can find out this relation from the note given in the last section of your chapter. Okay, from that A and B is like this. Therefore, substituting that A and B in this relation, you get it as, you take 2 mu and L to the right hand side and substitute for A and B. You get it as T square is equal to 4 mu square by L square pi square A square B square. Substituting A and B, you get it as T square is equal to pi square mu by 2C A cube. Okay, using A is equal to C by minus E, and C is equal to GMM, and mu is equal to MM by M plus M. On substituting these two values for C and mu, you can write the equation as T square is equal to pi square by 2M plus MG A cube. Okay, in this relation, T is the time period of the satellite and A is the major axis. So in the relation or in the third law we say that t square is proportional to a cube, right? But it is not exactly uh, the term in between is not exactly a constant. It is mostly dependent on, it is slightly dependent on the mass of the planet also, but it has a very small effect. Therefore, t square is equal to pi square by 2m plus mg a cube. This is not exact. That means t square by a cube depends slightly on the planet's mass. But even for a Jupiter, which is the largest planet, m by m is only 1 by 1000. So that Kepler's third law holds to good accuracy in the solar system. Okay, you can see different satellites and their value a cube by tq. It is approximately constant to some extent. To 1 by 100 term only, there is a difference for the a cube by t square value. So we can take it almost constant. There is one more way to find out the law of periods, that is from deriving or integrating this relation which we have studied earlier, the variation of r and t theta, r variation of r with t. Okay, that integration, in that u effect is applied and u is taken as minus c by r. Substituting all these terms and integrating, the list of integrals is listed in the standard table. For the special case when e is less than 0, we find tb minus ts equal to this much, and applying the limit, you get it. The final result, you get the same result which you have found out earlier. T square is equal to pi square mu by 2c a cube. Okay. So there are two ways to find out or to prove the third law, which is the law of periods. Kepler's third law can be proved in either of these ways. Okay.